אני לפני שנכנסתי לגיא ספידי שיעצתי יבש. הסתובבתי כבר, שלא יהיה את הנקודה,
יש הרבה עידוי, זה מה
העידוי, כן.
עוד שור פה. חצי דקה באמת, אני חושב שחבר לכם ברב שאתה...
כן. העליתי פשוט כל צער פרנקו, לא?
בסדר?
כן.
Okay, let's get started. It's a pleasure to have with us today Tom Goren from Bar University. Tom, some of you know, was here for many years for undergrad and graduate studies. Then he moved to Germany, to Leipzig University for a postdoc. Did a tour in the US and back to Germany.
Yeah, you can use this slide. It's a great circle. West or then back?
Nice.
Just realize that.
Yeah, and in the last 2 years is...
didn't make a stop in Green.
No, it just looks like.
Yeah, in the last 2 years he's an assistant professor at Bar University.
Thanks, guys. Yeah, so I will introduce two topics first. Cloud morphology, and then I will relate it to Aerosol-Cloud interaction. So I will start with introduction about cloud morphology, and then you will see through the slides how the two are connected. Yes, this doesn't work. So this is a satellite image of the world, and you see the continents, the southern ocean. See all these clouds over the oceans, and they have. You can see that there are overcast clouds and broken clouds and some other features. It's like huge, like flower clouds. If we zoom in, let's say into this area, you can see that there are different cloud morphologies. So we have these overcast clouds with thick clouds in the center, and then you have less brighter clouds around it. And we have these broken clouds. So we have thick clouds and... No, it's fine. So we have the overcast and broken clouds. But you see you can see different morphologies. We call these closed cells and these we call open cells. And if we want to take a scene, a given scene, let's say 100 by 100 kilometer, and to calculate the scene albedo, we take the cloud albedo and multiply it by the cloud fraction, and then we take the albedo of the clear sky, the ocean in this case, which albedo is nearly 0, it's 0.07, and multiply it by the clear fraction. And this gives us a linear equation, right? But in reality, when we do that, it's not linear. And this is because there is also in-cloud morphology. So we cannot assume that every cloudy pixel has the same albedo. We have cloudy pixels with high and low albedo.
How is this generated? This figure, how is
These are many scenes of different cloud regimes, open, closed cells, different combinations. And this is from LES simulation, but it looks the same from observations as well. And I will explain now. So if we zoom into the closed cells, we have these areas with, you see there, like thinner clouds, it's darker, and we have at the center brighter clouds. And this means that the albedo within the scene is not the same. So every cloudy pixel has different albedo. And the same in the broken cloud. So we have thick clouds, and then, far it's shaking. So here we have, it's hard to see in the screen here, but there are clouds that are really thin. You can see the ocean through them. And this is again the in-cloud morphology. So we have the cloud morphology of a cloud field, open and closed cells and other cloud regimes. And we have the in-cloud morphology. And this in-cloud morphology is overlooked in many studies. usually we talk about closed and open cells, but we don't talk about what's going on within the clouds in these regimes. So if we take a cross-section of these clouds, so on the right it's like from the satellite view, we look from the top. So these clouds, they have thick cores, and then they are rising and diverging. So the boundary layer is about 2-3 kilometers. So we have these anvil clouds, like thunderstorm, but this is much, much smaller. And these are the darker clouds. These are the cores, the brighter ones. And if we take a cross-section of the closed cells at the top, they are much thicker overall, but the cores are slightly thicker, and they team a little bit to the edges, but yeah, the clouds does not evaporate completely. This is why we have this field morphology of open and closed cells. So in this case, the cloud thickness actually controls the cloud albedo within the scene, the in-cloud albedo. And this work by Isabelle McCoy, they use machine learning to look on satellite data, and they classified cloudy scenes as into cloud regimes, open cells, closed cells, and they have other types, fog and disorganized, different cloud morphologies, but cloud field morphologies. And they show here the albedo as function of the cloud fraction. This is from observations, similar as before, but they show it for closed and open cells differently. And what they show here that for a given cloud fraction, open cells and closed cells, they can have the same albedo, the same cloud fraction. So for a given cloud fraction, we can have different albedos. So we can usually what studies state that we have closed cells, high albedo because it's overcast, and broken clouds, low albedo because they are broken. We have the ocean is exposed. So the albedo of this thing is lower than this. You can see it by eyes. But they say here, they show that it's not that simple. The albedo, even for a given cloud fraction, the albedo can change depending on the cloud regime. So it's not only the cloud regime, it's also the in-cloud albedo.
How do they define the open versus closed?
So they look on the liquid water path, which is comparable to the vertical extent of the cloud, and the skewness and all the statistical properties. They can tell whether the cloud has these thick cores and thin angles, or whether it's more homogeneous. Based on that, they could tell whether it's dynamics of closed cells or open cells. So this is an example. We have on the right side this cloud field, here this singular cloud field. Cloud fraction is the same, roughly the same. And is it open and closed cells? So this is classified with dynamics of open cells. You see that, well, it's hard to see, but the cores, we have like these are brighter clouds with the divergent angles. And these are closed cells. And the cloud fraction is the same, but albedo is different. So it's not, we cannot just say closed and open cells, as I did in my PhD actually. Then I was looking on transitions, and they related it to how it affects the cloud albedo, whether we have open cells or closed cells. Now I look into the cloud morphology, the in-cloud albedo. So that's again the cross-section. So this is dynamics of open cells, this is dynamics of closed cells, more homogeneous cloud field. And now aerosol-cloud interactions. So we can divide aerosol-cloud interactions into the cloud albedo effect, and this is how addition of aerosols increase the cloud droplet number, and then it increases for a given amount of cloud water, we have more droplets, so the surface area of the clouds is increasing, so the cloud is more bright. And aerosols can also affect the lifetime of the cloud. The cloud can live longer, or the cloud can have more cloud water. It can change its properties. The first part of the presentation will deal with thin cloud or cloud morphology and cloud albedo effect, or we call it also the Toomey effect. And the second part will deal with cloud adjustments, how the liquid water path depends, how changes in liquid water path with aerosols depends on cloud morphology. And these are two topics that were overlooked in the literature, even though they are super important. So just to remind you about cloud albedo effect, or again the Toomey effect, the most famous example are shipwrecks. So the aerosols from the ship goes into the cloud in the pristine oceanic regions, and they increase the number of droplets. the clouds become brighter. So you can see the brighter clouds here. This is thin clouds, and then the more aerosols make it more bright. It also changed the cloud water, but overall it makes it much more bright because we have more aerosols. And this reminds me of those trails in the desert where animals walk again and again and smash the gravel, and then it becomes smaller particles and its more albedo is increasing. Of course, there are biological crusts that are destroyed and contributed, but just for it's a nice illustration, I think, of this Toomey effect. And this Toomey effect over the ocean is not only due to shipwrecks. Shipwrecks, we put the aerosols there inside the ocean. We have every day, all the time, air masses from continents with anthropogenic and continental aerosols are advected, depending on the synoptic situation, into the ocean. So this is Spain and the UK up there. And in case of high pressure, there is movement of air mass from Europe into the ocean. So this cloud, I show that they are brighter because they form in polluted air masses. They have more aerosols. And we also quantify the contribution of the anthropogenic aerosols. So these clouds are brighter because of aerosols, anthropogenic aerosols. Now, we want to quantify the increase in albedo, this brightening effect of the clouds, because it affects the climate, right? If the clouds are more bright, the more energy is reflected back to space. So we use satellite data for that. Also modeling, but I will focus on the satellite data. From the satellite, we have level 2 data, and this is more this is typically used because we have high resolution data, and for over 20 years now. Now, the resolution is 1 by 1 kilometer, and you can see the cloud morphology here. You can see the thin clouds around these more pillow clouds. But this is a lot of data. It requires every scene here. It's hundreds of megabytes, and if you want to do a climatological study, you need many years over the globe. It's a lot of data, and it takes a lot of time, computing time. So MODIS also provide level 3, which is simply the means, all the means of level 1. So they take the scene mean, cloud properties, and then provide it as a grid of 1 by 1 degree. And this is what almost everyone uses. So they, level 3 ignores this cloud morphology. We take only one single value for every point. But it is, again, much easier to use level 3 because it reduces computational complexity. Also, it removes some of the noise because we have some uncertainties. We decide high resolution when we do the average, it goes away. And the way we calculate or estimate the brightening from the satellite observation, we use this cloud albedo approximation, susceptibility. It's the sensitivity of the albedo or the reflectance to the relative change or differential change in droplet concentration. So R is cloud albedo and D is droplet concentration. And beta is the albedo susceptibility. The sensitivity of the cloud albedo to change in droplet concentration. And this is a very simple equation. It depends only on the cloud albedo. So if you have the cloud albedo, we can calculate this value, and this is the function. So we have the susceptibility here and the albedo here. So it's a nonlinear function. So once we have the cloud albedo, we just need to assume what is the change in droplet concentration. So let's say, what is the change in droplet concentration due to anthropogenic activity? So what is, how much more aerosols with respect to the pre-industrial times we have today? So we have this value here. This is also a challenge to know what is this value. But then we simply multiply it by this, the number we get here, which depends only on the cloud albedo. So we observe the scene of 1 by 1 degree. We have the beta here, the cloud susceptibility, and we multiply it by our whatever change in aerosols that translate into change in droplet concentration with respect to the pre-industrial time. Now, here you see three scenes, three 1 by 1 degree scenes of these clouds. Do you think the mean cloud albedo is the same? I would guess that maybe this has lower albedo, this might have higher albedo. you clearly see different cloud morphologies with respect to the in-cloud, different in-cloud morphologies.
Now, how do you guess that? Or do you guess that
I just guessed. I know the answer. The answer is yes. The main cloud albedo is the same, but just by looking on the cloud scenes, you think that the albedo is not the same. Maybe here the albedo is even lower. You can argue because we have many thin clouds that they are darker, but the darker clouds are compensated by the brighter clouds. So this is already open cell, those deep coarse thin angles, cloud morphology, the field morphology. These are closed cells, very homogeneous clouds. You see the distribution here of the reflectance in the 0.6 micron, which is very similar to the cloud albedo. So here the distribution is much narrower, while here it's much more, we have this skew to the skewness here is due to the T-cores. But the scene mean albedo is the same. So the albedo susceptibility for these three scenes would be the same if we use this equation from before. But you already, I assume you guessed that this is wrong, because we need to take a weighted average, right? So let's go back to this illustration of level 2 data. We have 1 by 1 kilometer information of the cloud albedo within this 1 by 1 degree scene. Level 3 takes the scene mean, one value, and then we get from level 3, as all the studies do, they get one value, let's say 0.080 for this. But what we should do is take the weighted average. So we need to take the high resolution data and calculate the susceptibility for every beam of albedo, and then do the weighted average. And as I will show you, it's always lower than the one that all the studies report. So there is a systematic overestimation of the Toomey effect from studies that use this equation in level 3. And next we wanted to quantify the susceptibility bias, the bias due to the different resolution. So beta star, this is the bias, and it is the difference between the susceptibility that we get from level 3. This is the bias one, as most of the studies do, minus the true susceptibility that we get from level 2, as if we do the weighted average, and we just divide it by the true one. And next we also need to quantify the inhomogeneity or the cloud morphology of each scene. So for that we use the interpercentile range. It is the difference between the means of the upper percentiles, or upper 30 to 33% of the scenes, minus the mean of the albedo in the lowest percentile. So for homogeneous clouds, the difference will be smaller, while in these more homogeneous clouds, the difference will be larger because the distribution of the albedo is larger. If we have this skewness to the right with the T-cores, this will affect the interpercentile range, delta R, the difference between the upper and lower percentiles. And these are the results. And I also will guide you through these plots now. So here on the left side we see the bias, the susceptibility bias. In the x-axis, this is the scene mean albedo, and in color, this is the interpercentile range, or this is a measure of the cloud inhomogeneity. More red, higher values means the clouds are the T-cores and T-angles. More blue means the clouds are homogeneous everywhere. So you can see that first, let's start with scene mean albedo of 0.5. This is 1 year of data, observations from models. Let's start with scenes of 0.5. You can see that as the inhomogeneity increases, the bias is also increasing, and you can see it in this function. So if we have scene mean of 0.5, for sure not all the pixels have a bit of 0.5. We have distribution, so for sure some will be above 0.5 and some will be less than 0.5. So they push the true susceptibility down to lower values. And if we increase the inhomogeneity, the interpercentile range is increasing, the bias is increasing because we take more and more pixels down here and the slope is increasing. So the bias is increasing. And look, it can be as high as 40 or 50%. This means that there is a bias of 50% in the brightness of the clouds that's estimated. That's quite a lot. And so this is what we call the dispersion effect. And we have the nonlinear effect. They are both connected, of course, but most of the clouds sit here from climatology. We don't have seeing beams with albedo 0.7 or 8. It's not likely to have 1 by 1 3 with so bright clouds. Most of the clouds sit here. And here again, we have a Siemens albedo 0.3. So you see that we have the distribution, and the clouds to the left, they go down, they drop down quicker than those to the right. So there is no compensation. Compensation never occurs. Only in very small number of cases where we get the opposite underestimation, but this is negligible. Most of the clouds is during the positive bias. And also here, if we increase the homogeneity, the interpercentile range is increasing. So the lower percentile drops farther down, and this becomes slowly increasing, and the bias accordingly increases. And the average, global average of the bias is about 10%. This is quite high. I will go back to that later. So here I show you in the y-axis, this is the albedo of the upper percentile, and this is the albedo of the lower percentile. And now in color, this is the bias, up to 50-60%. And you can see that the largest bias is at the top left, where we have thick cores with high albedo in the upper percentiles, and thin cores with the low albedo in the lower percentile. And those clouds that sit along this one line, they are homogeneous. It means that the upper and lower percentiles are really very similar, like here. The difference between the percentiles is very small. So these are homogeneous clouds here. We never get fully homogeneous clouds, but close to that. And here, where the bias is high, we have these inhomogeneous clouds, so thick cores and thin angles. And these clouds are common in some regions of the oceans. And another interesting aspect that came from this analysis, here we see again the seeming albedo of the upper percentile and the seeming albedo of the lower percentile. Now look at these 2 points. If we go along this line between the 2 points, the albedo is the same, right? It's the same color, albedo of about 0.4, 0.5. It means that the thicker the cores, the thinner the angles, because they compensate each other to have the same seeming albedo. Now this must be, if we take the percentiles, we must compose the average, right? But we see this also from other studies, from LEL simulations and other methods of analysis, that the seeming albedo along the transition from these homogeneous clouds to these broken clouds is roughly similar. The albedo is the same. So it is the change in cloud morphology and also in the droplet concentration that affects the Toomey effect that have very robust and pretty consistent albedo along the evolution of the clouds. And this evolution of the clouds is the transition from stratocumulus, from overcast to cumulus clouds, broken clouds. This is the transition from closed to open cells that occur in the subtropical oceans, and there are many studies that try to understand how aerosols or global warming affect these transitions, because the cloud fraction is controlled whether it's closed cells or open cells. And just to mention that we also provide a correction for this albedo susceptibility bias. This correction is very simple. We just need to take the standard deviation of the albedo we didn't even see. But it is not straightforward to apply it's not straightforward thing to do, because MODIS do not provide us the standard deviation of the albedo. They do provide with the level 3 the standard deviation of liquid water bed, effective radius, and other parameters. But for some reason, they don't provide the standard deviation of the albedo. And I hope that in the future they will include it because more and more studies show that this in-cloud morphology is important. And if we, in the level 3 data that everyone used, would have statistical information on the albedo, that will allow also to explore more things and to correct this albedo bias. So to summarize this part, the first part of the data aggregation, I showed the special aggregation of satellite data into commonly used gridded formats of 1 by 1 degree typically. It leads to an average 10% overestimation of the albedo susceptibility. And just to put this in context, this bias is about 0.7 to 0.1 watt per square meter globally. And this is more than double. This is larger by 2 orders of magnitudes than the positive radiative forcing attributed to contrails. You know, thin clouds from like contrails, those contrails in the sky from aircraft, they warm the climate. And there are studies trying to quantify this warming and showing that this is significant, the warming. But this 10%, even though it's 10%, it's larger than 2 orders of magnitude than the warming due to contrails.
How did you translate from changes in susceptibility to radiative forcing?
So we take this 10%, we can simply multiply all the estimates of the watt per square meter.
So you did aggregation here, right? So basically, because the change in the orbit number concentration won't be fixed everywhere.
Right.
So you need to calculate the bias in susceptibility,
Yeah.
to multiply by the change in aerosol in a given location.
So we did a correction.
Okay.
We did a correction for the change, yeah, and then we compare it with the numbers that are reported. In the IPCC, for example, they report these forces.
Oh, and then
and the difference is that, or the ratio is that, yeah.
The change in 10% in susceptibility, but it's also 10, it's linear, it's also 10% in the radiative forcing?
Yes, I need to check that. It's a good point. But we didn't go this path that you described. We calculated it separately. And the second point, the overestimation can reach up to 50%. This is large. So average is 10%, but in some cloud regimes, cloud field regimes, it can be 50%. And this is due to neglecting the subgrid or the in-cloud heterogeneity. We propose a correction, but as I said, it's not straightforward because we don't have in level 3 this data that everyone can simply correct their observations. And also, this is important for marine cloud brightening. So in Europe, it's more conservative if I'm talking about marine cloud brightening, but in the US, there's a lot of study about that. If we want to operate cloud brightening, so we need to have a forecast of the clouds in different locations, see if they fit to cloud brightening. So to get the most effective outcome from brightening the clouds, we need also the in-cloud morphology, because if the focus will give us a scene mean albedo of 0.5 or 0.3, and then we say, okay, we use this equation and we see how much brightening we have, we need to know the actual brightening. So we need to account for this in-cloud morphology, to know how effective it would be.
Tom, before you move forward, are you done?
With this topic, yes.
So how dependent are your results on the presumed form of the data as a function of the R? I couldn't figure out what exactly you assumed there. Is it an assumption?
We assume that the cloud is homogeneous.
But ND, you assume a relationship between ND and R?
There's a relation between the relative change in ND,
Right.
yes, and the change in the reflectors, in the albedo.
Why would it be independent of, why would it be such a weird function of R?
I can show you the deviation of this expression.
What assumption are underlying this transition? What do you assume?
We assume homogeneous cloud,
Okay.
and so if you take the geometry of the clouds, and you can see how the albedo would change. I mean, it's very simple equations. It's actually, to me, he came up with this idea of cloud brightening. It's so simple because we just take a volume and divide it into smaller droplets. Everyone, kid in school can understand that. It's so brilliant. It's so simple, but it's 40, 50 years people talk about this, and still still explore this effect.
Okay.
Can I interrupt something?
Yeah.
So about the 50%, the second point. Am I wrong about this, or is this like, for example, measuring the length of a shoreline? Like it's like a fractal issue. So can you? So is it like a similar thing here? You can actually get an estimate for the error that by comparing, building it into 5-degree bits versus 2 versus 1. But you don't really need to have all the data. There's maybe some correction that is just because of this grain binning it into homogeneous.
So if I understand it correctly, you refer to the frequency of occurrence of different clouds that has high bias or low bias, right?
Not
So-
low bias versus high bias, but if you just the resolution, maybe I'm wrong about this, but if you're just binning it into say 1-degree bins, you're assuming the homogeneous part, right, and then attributing a value to each of these bins, right?
What?
Right? And then
Which value? What?
the cloud fraction.
Okay.
Or whatever.
Yeah.
But then you're missing out on the details. And
Yes.
And the higher resolution you would go, right, you get a more accurate value. That's like trying to measure the length of the shore and the higher resolution.
Yeah. Okay.
Right?
Yes.
What I'm saying is, could there be like a similar approach to this, and seeing how that is changed by changing, the way you aggregate frequency,
Yeah.
different
Yes.
bit sizes, and then coming up with an approximation to basically in the
Mhm.
asymptotic limit of
Yeah.
getting, an infinitely small bin. How should it look like?
I understand. So there are studies that were done in the past few decades ago showing the sensitivity of this albedo approximation, but in the pixel size, like in 1 by 1 kilometer. But no one projected it into like practical use, like we do with level 3 and level 2, or like we take level 3. No one related it also to cloud morphologies. They just looked on the pixel inhomogeneity, small scale variation of the albedo. And this is different than what I show here. The concept is the same. So of course, if I do aggregation first, like half by half degree, 1 by 1 degree, and so on, it will probably saturate at some point. But also we need to be careful not to take too large areas, because then we can mix in different cloud regimes into the one scene, and this might also affect the results. So now let's move to the second topic. I will focus on thin clouds. Only the thin clouds. So they are called veil clouds because they are super thin and they look like this veil. You can see the ocean through them. For example, here you see the dark ocean below. And they are these divergence angles from the cloudy course. And they are very common in the stratocumulus to cumulus transition. So this is the Southeast Pacific, and we have these overcast clouds, closed cells, and then they break to open cells. And these open cells, or other types of organized convection, they have these veil clouds. So they are very common in these regions. 50%, sometimes even more. 70% of the scene is composed by thin angles. And here, this is illustration of this climatological transition of the stratocumulus to cumulus. And the boundary becomes steeper. We have these overcast clouds, and then thick clouds, thin angles. Remember I told you that the thicker the course, the thinner the angles. So we see along this, the evolution of these clouds here. And these clouds are also, they're called ultra clean layers because they're super clean. So this is the cloud. It's only 2 kilometers. It's not a thunderstorm cloud. There is going up here, and there is a collision coalescence and precipitation formation processes. So the air becomes clean. There's rain. The rain washes all the aerosols, and only the few drops that didn't fall down, they are diverging at the cloud top and create these thin, ultra clean layers. So they're clean because they were washed by precipitation. The droplet concentration, the ND is very low. It's like 10, 20, 30 in these clouds. And we wanted to quantify the fraction of these thin clouds. So previous studies just took a cloud optical thickness threshold, smaller than 3. So looking on scene, and then all the clouds with optical thickness, all the pixels with optical thickness smaller than 3, they counted those clouds, those pixels as thin clouds and calculated the fraction of thin clouds. But the problem with MODE is that these clouds are super thin, so the cloud retrieval algorithm doesn't work for them. So many large fraction of the thin clouds, they don't have optical thickness. This means that using this method underestimate the fraction of thin clouds. So we corrected this by looking on the pixel, the reflectance in every pixel, and we had all these pixels that had some reflectance that is larger than the ocean, but didn't have retrieved cloud optical thickness. We assume they are thin, because they are for sure smaller than the pixel that has, they are sure thinner than, or they for sure have smaller optical thickness than pixels that do have successful retrieve optical thickness. So you can see the difference here. We have this cloud scene, and this is the modest retrieved cloud optical thickness, and this is our correction. So these clouds here, they are thin, they don't have cloud optical thickness, but they do have reflectance. And their reflectance is smaller than the reflectance of these thin clouds here, so we assume they are thin. So we reconstructed all the thin cloud fractions. And this way we came up with a much more accurate thin cloud fraction than in previous studies. And we looked on the radiative effect of these thin clouds. So at the beginning of the presentation, I told you that we can have I showed you that we can have the same cloud fraction, but different cloud albedo. So we want to see how the thin clouds affect this cloud albedo. So on the left side, you see the fraction of thin clouds. You see it goes up to almost 90%. 90%, 0.9. Almost 90% of the scene can have only thin clouds. And this is the cloud fraction here. So the thin clouds are part of the cloud fraction, of course. And in color, this is the short wave, the cloud radiative effect. The cloud radiative effect shown in color, these are the numbers, are negative because this is the difference between the radiation that goes up without any clouds, the radiation that goes from the surface, from the ocean up, minus the radiation that goes up from the cloud. And the cloud is brighter from the ocean, so there is more radiation going up, right? If you take the difference. This is why it's negative. So if we go back to this figure and we look at a given cloud fraction of 80%, 0.8, the more thin cloud fraction, the less energy going up to space, because the cloud is transparent. So we have the core, and the core is thick enough, it is white, we saw in high albedo, so it reflects most of the radiation, high albedo. But the thin clouds are thin, so some of the radiation can go through them and some can be reflected back to space. And we did the same for the long wave. So the long wave is neglected in shallow clouds like here because the clouds radiate based on its cloud top temperature. So the long wave is important for high cirrus clouds because they are really cold, so they radiate based on the Stefan-Boltzmann law, and they are colder, so they radiate less. But if the clouds are close to the temperature of the surface, they radiate more or less like the surface, so the effect of the warming, the radiation that is projected, radiated downwards from the cloud, based on the cloud temperature, is less important because it's similar to the surface. Nevertheless, we find that it is not negligible. So the cloud radiative effect here for the long wave, it's again defined as the difference between the long wave radiation going out minus the long wave radiation with cloud. So this is smaller because the cloud is almost colder than the surface, so it radiates less. And here we see the thin cloud fraction as a function of the cloud fraction. In color, this is the long wave, the cloud radiative effect, watt per square meter in the long wave. For a given cloud fraction, as we increase the thin cloud fraction, we go towards lower values. It means that more radiation is escaped to space, meaning that the cooling is larger, or there is less, let's say there is less warming from thin clouds because they allow the radiation to go back to space as it comes from the surface.
Tom, can I ask something?
Yeah.
So I'm not sure how can you get a cloud fraction of 0.5 and thin cloud fraction of point.
Yeah, so this is the fraction of the from the cloud fraction. The fraction from the cloud fraction. To illustrate that, we have these thin clouds, the veil clouds, so the radiation from the surface can penetrate through them and then go. And of course, there is also the cloud itself radiates, but it allows more radiation from the surface with a higher temperature to go back to space. It doesn't block it, it doesn't absorb it, and then re-emits it with a lower temperature. And there's a few degrees temperature difference, so it is not significant. And they compensate each other. So we have more warming because of the thin clouds. They allow more solar shortwave radiation to reach the surface, but they also allow the surface to cool more, so it balances the warming. So they compensate each other. So here we see the thin fraction as function of the cloud fraction, and in color this is the long wave compensation. And it can be up to 20 degrees depending on the fraction of the thin clouds. And when we estimate the cloud radiative effect of warm clouds like this, we, at least from observation, we neglect the long wave. We just look on the short wave because this is what matters. The long wave is negligible because we assume the cloud top temperature is similar to the surface, so it's not that important. We show that it is important, especially in some cloud morphologies where we have high thin cloud fraction.
So what's FC? What are the contours?
The colors, this is the compensation. This is the ratio between the long wave and the short waves that I showed before. So now how it links to Aerosol-Cloud interactions. So here we see two scenes of open cells. These are two scenes of open cells. But the droplet concentration in these two scenes is the same. These are precipitating clouds, so the clouds have low ND, low cloud droplet concentration, but the liquid water path is different. Here we have much more thin clouds. You see all these stratiform layered clouds. These are thin clouds, and these are ultra clean. They have low ND, like those precipitating clouds have low ND. But when we calculate the mean cloud water within a scene, we count for all the pixels with cloud. All the pixels without clouds, it's none. We don't consider them. So when we do the weighted average, like we do an average of this cloudy scene, the droplet concentration will be the same, but the liquid water path will be smaller here because it's low because we have many thin clouds and they are thin. They don't have much cloud water. So same regime, but liquid water. The only difference between these is the liquid water path and also the albedo to some extent. But here I want to show that the weighted mean, the way we average the cloud properties within a scene. If we have more thin clouds, it will affect the average mean, the spatial mean. And you see it here again, that F thin is function of cloud fraction, and this is the liquid water path in color. For a given cloud fraction, the more thin clouds, the less is the liquid water path in the scene. And this is actually underestimating this gradient, the effect of the thin clouds, because as I mentioned before, we don't have observation for optical thickness in thin clouds. We also don't have observations for the liquid water path. But it's much more difficult to fill in the liquid water path with realistic values. So now we use machine learning to fill in all these missing pixels in the satellite views and satellite data, the LWP, the liquid water path of the thin clouds, and the gradient is larger than what I show you here. And this is important because liquid water path sensitivity to droplet concentration is one of the things that many of in my community talk about recently, because there are many different many studies that show different values. So sometimes the liquid water path increases in one study that uses one methodology, and the other one it decreases, and the liquid water path is proportional to the cloud albedo. The more liquid water path, the thicker the cloud, so the optical thickness is larger, the albedo is larger. And this is one of the greatest uncertainties in Aerosol-Cloud interaction, understanding how the liquid water path would change to aerosols or to droplet concentration. And I show you here that if ND is the same as in the example before, the mean L, the liquid water path, depends on the thin cloud fraction. So if we do not account for the thin cloud fraction, we get different values here, right? Just it's a function of the thin clouds. So this is not. It does just looking at this as is from satellite data. It has no physical meaning if we don't account for the thin cloud fraction as a confounding parameter that affects the L. Yes, so thin clouds control the liquid water path sensitivity to droplet concentration, and this is my last slide before the conclusion. This is examples of many studies in the past years. 2019 it started with Ed Griffith, who was a co-author on that, and then LES simulations later on, and this is from satellite observations and looking on the biases from satellite observations. And this is from GCM, and the axis in all of these plots is LWP as a function of ND. And we get different slopes, and every study tried to explain why it is different from the other one and trying to look on comparability with meteorology or biases in the satellite retrievals. But at least one aspect is the thin cloud fraction that affects this whole story, because it changed the LWP dramatically, as I showed you. And if LWP depends on thin clouds, then depending on the data we observed, it can be anything. So this is a work I just submitted this week that focus on the thin cloud, how it affects the liquid water path susceptibility to droplet concentration. So to summarize this part, thin clouds, they modulate the short wave and long wave. Thin clouds modulate the short wave and long wave components of the cloud additive effect. And by the way, in GCMs, we don't have cloud morphology at all. We just have one value for the green part. At least the more conservative, like those GCMs that do not resolve with not high resolution GCMs. And thin clouds, they dim cloud brightness by up to 65%. They make them less bright for given cloud cover. Thin clouds reduce the long wave warming by up to 50%, as I showed, and they modulate the balance between the long wave warming and short wave cooling. And thin clouds also control the seeming cloud properties, which can affect assessments of aerosol-cloud interactions, like liquid water path adjustments. And the two works were published already, the two parts, and the third part is on the way about the LWP adjustments. Thank you.
You take into account the elevation of the clouds?
The what?
The elevation. How high?
Yeah, no, we looked at the cloud top temperature as well, which this matters for the long wave cooling, the cloud top temperature. And it is, the results are the same. The cloud top temperature is actually roughly similar across the regions of the subtropics, because in the eastern part, where the boundary is shallow, but the sea surface temperature is low. And then as the clouds go into the deep ocean, the remote ocean, the clouds grow, they become thicker, higher, so they cool, but also the sea surface warms. So this warming of the sea surface temperature compensates for the cloud height, so overall the cloud top temperature doesn't vary much. So this.
I'm asking if different shallow clouds at different elevations have different properties.
Yes, so we do everything, and it's between 1 to 3 kilometers, shallow clouds. And my first answer was with respect to the cloud top temperature, which I think it's matter to the long wave. This is why I thought you were aiming to that.
So this poses, so you're adding degrees of freedom to how we should represent clouds and models. Mm-hmm. So what are just your thoughts about this? How is this a solvable issue in terms of representing clouds and cloud models? Because you're saying that we should differentiate between thin clouds, right, and thicker clouds.
Yeah. So we can look at the distribution, like to have some property of the distribution of the albedo or the LWP, the liquid water path within scene. And this distribution depends on droplet concentration, on boundary layer depth. So maybe we can come up with some relationship for this morphology based on other properties that GCMs provide us with a reasonable accuracy. So we see more thin clouds in deep boundary layer with low droplet concentration,